Bismillah ar-Rahman ar-Rahim. Last time we started the unit of other gate types, okay? And we started talking about the buffer and tri-state buffer, okay? And we said that the buffer is used for amplifying the output signal and to give it more drive power, okay? And the tri-state buffer is used when we want to share a bus, okay, with several devices, okay, so that or several circuits, so that it can be used for read and write, okay. And we give examples of 2 devices sharing the same bus and 4 devices sharing the same bus, okay. Today we are going to talk about NAND and NOR gates, okay. We have seen them very briefly before, but right now we will cover the details of them. So the NAND gate, to start with, is composed of an AND gate followed by a NOT, okay? And we, in order for, as because this NAND gate is used a lot, okay, we created a symbol for the NAND gate by itself, okay, a symbol for the NAND gate instead of just AND followed by a NOT, okay, we create a symbol for the NAND, which is basically a pure AND, okay, with a little bubble at the end to indicate that this is nothing but NAND gate, okay? And this representation of the NAND is called AND NOT representation, okay? So the bubble at the end, as I said, represents or corresponds to the inverter part, okay? Algebraically speaking, Z, okay, is equal to XY and the whole thing complemented. And if you apply De Morgan's law, who can tell me what is this in using De Morgan's law?
X complement ORed with Y complement.
Excellent. X complement ORed with. So there is so the AND gate, the NAND gate can be represented with an OR gate. You see, you can say, well, take the complement of the inputs and then feed them to an OR gate, and then this is equivalent to an AND gate. Okay, so there are 2 symbols for the NAND gate. One is this symbol, and the other symbol is this symbol here. Okay, don't be fooled by the OR gate here. Okay, since you have inverted the inputs of the OR gate, okay, it is basically, this is exactly a NAND gate. Okay, instead of having the complements on the input, we put bubbles at the inputs of the OR gate. So this form of the NAND gate is called the NOT OR form. Okay, NOT OR form is another form or another symbol for the NAND gate. Okay, so you can think of this. Okay, you can think of this as, okay, if I just make this smaller, as if, for example, this bubble has been pushed back to the input, okay, and the pushing back has scooched or squashed the AND gate symbol, and it became an OR gate. Okay, it has distorted, let's say, distorted the AND symbol, okay, which is a half circle, and it became like an OR gate. Okay, so the pushing back of the bubble becomes like this. Okay, or you can think of it as pushing the bubbles in front. Okay, and then this will convert this to AND. Okay, so just think of it like this, and you will realize that. I mean, you will visually link the 2 shapes together. Okay. All right. Okay, some properties about the NAND gate. It is commutative, meaning that X NAND Y is the same as Y NAND X. Okay, it's the same, right? But it is not associative. Okay, it is not associative. Okay, so this X NAND Y, and then you take the result and NAND it with Z is not the same as a 3-input NAND gate. Okay, if this is F1 and this is F2, then F1 does not equal to F2. Okay, because the NAND gate is not associative or associative. Okay, and it is a good exercise for you guys to prove the non-associativity of the NAND gate using either converting the both sides here to canonical form, okay, or deriving the truth table. Both ways are equivalent, or you can also minimize them to the least what we call standard form, okay, either sum of product or product of sums, okay, and they must, if they are equal, they must be the same. The two expressions must be the same modulo the order, of course, the order of the products or the sums, okay. All right. However, a cool feature of the NAND gate, a cool property of the NAND gate is that it is universal, okay? And universality is the best thing about the NAND gate, okay? What does universality mean? Okay, we have a definition here. Okay, a universal gate, or a set, a universal set of gates, you can say, if there are more than one, okay? But here it's only NAND. A universal gate is a gate that can be used to implement any Boolean function. You can implement any Boolean function using this gate, okay? So for example, we know that any Boolean function can be implemented using and, or, and not, right? So we know that and, operation and, operation or, and operation not constitute a universal, a set of universal gates, okay? Universal or universal. All right, by definition, because we can implement Boolean functions using these three operations only, okay? So my question to you, if I drop the not, I say, well, you can use and or as many as you like. Can you implement any Boolean function? The answer is no. For example, the simplest function is the inverter function. Okay, if I want x if I want x invert, which is a complement of x, I cannot do that with and or. I have to have the not operation. Okay, so the not operation is a simple operation that cannot be performed without having the not gate. Okay, but if I tell you, what if I drop the OR gate? Will the gate still be universal or not? The answer is yes. Okay, because we know that because this is nothing but you can think of it as an AND, because it's an AND followed by a NOT. Okay, and we told you that the NAND is already universal. Okay, so in order to show universality, you need to show that the NAND can be used to create the what we call the three gates, not, and or. If it can be used to implement these three gates, then we know that we can implement any Boolean function using this gate, this NAND gate. So now our objective is to show or prove the universality of the NAND gate. Okay, so here is the first step. Okay, the first step is to show that we can implement the NOT using the NAND gate. So if you have an X and its complement is Z, okay, then you can simply duplicate X, okay, as the inputs of the NAND gate, and the output of that will be Z, okay, and this output will be X complement, in fact, because it is eventually going to be X ANDed with X, and the whole thing complement, and this one here is nothing but X. So this produces X complement. Another way to do it, if you want to also be flexible, is to have X with 1. Okay, and then this will be X and with 1 complement, which is X complement. You see, this is another way of doing it, but this way is enough for us. Okay. Now, how to implement? So we know that we can implement the NOT operation using NAND operation, right? So we can, if we use the NAND operation, then we can get rid of the NOT gate. Okay. Now for AND, how can we prove that we can implement the AND using the NAND operation? And okay, can be implemented using NAND followed by an inverter, because eventually an AND is nothing but AND followed by an inverter. So all we have to do is to cancel that inverter. Okay, and we know how to implement an inverter using NAND gate. This is the way. You see? All right. So this is how we implement an AND gate. So if we have an X ANDed with Y and the answer is Z, then we have to use an AND gate instead, and then complement its result to get Z. Okay, so the two complements will cancel each other, and then we will end up with X ANDed with Y. For the OR, it's more involved, a little bit more involved, because we need to use the De Morgan's law here. Okay, De Morgan's law. So first of all, the OR gate, okay, is X ORed with Y. This is Z. Okay, I'm going to do a series of transforms to convert it to NAND. Okay, the first transform is to have to insert inverter here. Okay, and complement this. So if you think of this, if this is X complement, okay, and then you invert it, then you did nothing, right? It's the same as X. So the output here is X, and we still have the OR gate here, right? So the output here is still X or Y, right? We haven't changed the circuit using this. Are you following, guys?
Yes, yes.
Okay, so X complement invert is X, and Y complement invert is Y. So the final result is X or Y. Okay, it's the same as this one. So we haven't done anything to the circuit here. Now, if I take this inverter and convert it to a bubble here, and this inverter and push it and put it as a bubble here, then we have X complement, no NANDed with Y complement, because this is nothing but the other symbol of the NAND, right? Remember the other symbol of the NAND? What is that? This is the other symbol of the NAND, okay? Which is the NOT OR symbol or variation of the NAND gate, okay? So eventually this is nothing but X complement NANDed with Y complement, okay? So I can convert an OR gate like this to NAND by complementing the inputs, okay? And changing the OR to NAND. You see that? Okay. So now the next, for the examples that are coming up, they depend on your understanding of these operations. So please, if you are in doubt, please let me illustrate further. Otherwise, let's move on. Okay? Any question? Okay. So now the objective here is to, for example, convert a given circuit, okay, into NAND gates, okay, only NAND gates. And by the way, I haven't told you the reason for that. The reason why are we interested in changing a circuit to only NAND gates or NOR gates? What's the big deal here? Anyone can guess the reason for that?
Maybe lower the hardware, I think.
Yeah, it is. It is. In fact, it is related to your hardware. Excellent. Yeah. So eventually, when you are like a circuit engineer and you are developing some VLSI circuits, okay, and you are about to lay out your design on a chip, most likely that you'll have access only to certain what we call cells, okay? And these cells, for example, contain only, for example, from logic, they contain only NAND gates, okay? They don't contain or AND or inverters or something like that. Only NAND gates, that's it. So you have to constrain yourself using these gates, okay? So this is why we are teaching you how to do that. Okay, so now we study given a circuit. Okay, what are the steps to convert it into NAND gate? Okay, only NAND gate. Okay, the first step, okay, or the first thing that you need to do or you need to make sure is that no matter what you do, okay, no matter what you do, you must ensure that what you are doing does not change the functionality of the circuit, okay? It does not change the functionality of the circuit. So if you add an inverter, then you need to cancel it somehow so that you maintain the same functionality of the circuit. If you don't do that, if you add an inverter without canceling it, then the function of the circuit will change, okay? So this is the most important step. Whenever you do something to the circuit, you must cancel it somehow, okay? This is step number one. Step number two, first of all, you locate the AND gates, okay? The pure AND gates, and they are the simplest to convert to NAND. Why? Because all you need to do is to add a bubble at the end, okay? And then cancel it using an inverter, okay? So the functionality is still, after this, is still an AND gate, a pure AND gate. Because we have canceled the bubble here, but we still have implemented this using NAND gate, okay? Now for OR gates, we put the bubble at the input, okay? At the input, and then cancel them. So we cancel the bubbles here, okay? So this becomes an AND gate, okay? NAND gate. This becomes a NAND gate preceded by inverters, okay? So still the final result is still OR gate, okay? All right. Now in this step, okay, in this step or this step, maybe the circuit already have an inverter without a bubble, okay? So it already have as part of the circuit, maybe it has an inverter after the AND gate. So in this case, if it does, then you use this inverter, okay, to convert the AND gate, the pure AND gate, to an AND gate, just by pushing it back to the and changing it to a bubble, okay? The same applies to this scenario here. So maybe you already have an inverter, so you don't put a bubble here and then invert it, okay? But rather you use this as your bubble, okay? Finally, we have to worry about fan out branches, okay? Fan out branches, we have to worry about them because you will have to make a choice here, okay, to choose the option that results in the minimum number of inverters. So for example, if you have this circuit here and you would like to change this into a NAND gate, all right, then what do? You have two options. Either push this back, if you want to push this back as your bubble for this AND gate, okay, but then if you push this back, this fan out branch is okay, but you have to make sure that these branches are not affected, okay? So you have to invert them to maintain the same functionality of the circuit. Do you see that? Okay. So this option here results in how many inverters? This option here results in 1, 2, 3 inverters. Okay. Which is 2 additional inverters than the original. Okay. Or the other option is to add a bubble here, keep this as is, and add a bubble here, and then cancel it out using an inverter at the stem of the fan-out branch. Okay? So now, how many inverters do we use here for this option? Just 2, okay? Or 1 more inverter other than the original one. Okay, so here we have 3, and here we have 2. So this option here is clearly a better option. Okay. With that having said so, okay, we have to look at the big picture. Okay, because maybe these inverters, okay, will be input to OR gates, okay, that we can utilize later, and then reducing the total number of inverters, okay, and thus, even though locally this produces larger number of inverters, however, globally, to look at the global circuit, maybe this produces lower number of inverters in the global circuit. Okay. Any question? So now it's time to switch to examples. So we have this circuit now, and without simplification, we would like to show the NAND implementation of this circuit. Okay. And we would like to use the minimum number of NAND gates. Okay. Now in this question, we are asked to use only NAND gates. Okay. So we cannot use inverters. Okay. If the question says the minimum use and NAND only and minimum number of inverters, then it means that it is okay to use inverters. But in this question, it's only NAND gates. Okay. But we will use inverters during the conversion process, and then for the final version, we will convert these inverters into NAND gates. Okay, so let's copy this circuit to work it out using the steps that we mentioned. So let's start with as you see here, step number 1. Okay, what is step number 1? No matter what you do not change the functionality of the circuit. Okay, step number 2 is to start with AND gates and change them to NAND gates. Okay, so we start with AND gates and change them to NAND gates. I will use a different color for that. So I have this AND gate, so I change it to NAND gate. But in order to preserve the functionality of the circuit, I need an inverter, right? I need an inverter to cancel the effect of this bubble here. Okay. All right. What about what's next? Other AND gate, which is this one. I need to cancel it, and this is my F. You guys are following, right?
Yes.
Yes.
All right. Now what is remaining?
OR gate.
The OR gate. Okay. How do I proceed with the OR gate? I need to, you see in the OR gate here, what do? We need bubbles at the input, right? The input of the OR gate. Okay, and then we need to cancel these bubbles. For this input of the OR gate, for this input, we already have an inverter here that we can utilize, right? So I'm going to cross this inverter here, okay, and put a bubble here instead of that inverter. Okay. For this one, now this is part of a fan-out branch. Okay, so I'm going to copy the circuit here, okay, and draw the two options. Option number one. Option number one is to put a bubble here and then an inverter here. Okay. So how many inverters in the circuit now? 3 inverters. Okay. Option number two. Option number two is that I utilize this inverter by pushing it back. Okay. For this input. Okay. So if I push this back, okay, then I need to put an inverter at the stem. Okay, so let me just cross this out. Okay, and I need an inverter here. Okay, but in order to maintain the circuit functionality, I need an inverter here to cancel the inversion. Okay, but I can do this with the bubble here. Okay, so convert or compare the number of inverters between the two options. Which one results in a better or minimum number of inverters? Clearly, the second option, which is
Second one.
yeah, the second one, which is 2 inverters. So I'm going to erase this one. Before I erase it, is it clear, or do you need to?
How many inverters in the first one?
In the first one, count them. 1, 2, 3, right? We have canceled this, right? Now these bubbles, you don't count them because they are part of the NAND. They are part of the NAND gates, right? And this one as well. Okay, so 1, 2, 3. However, in this one, in the bottom one, 1, 2. Do you see that?
Yes.
Okay, so let me erase this one, the suboptimal one, and get this, move this up so that I have some space to draw the final circuit. So my final circuit is this one here. So this OR gate is converted to NAND. And then finally, I have, okay. Remember that I need to convert everything to NAND, okay? Okay. Yeah, so this is the final answer here. This is
Doctor, what did
actually,
you do?
yeah, actually I forgot to change this to, is this what you're referring to?
Yeah, I was confused of why you changed the last one and not the first one.
Yeah, just like that, okay? All right, so this is my final if, okay? This is because the circuit doesn't tell you to use inverters. But if the circuit says it's okay to use inverters, then it's okay. Like this one here. This is an exam question. It's major 2 of 191. Okay, question 2. And it says here, you can see that redraw the above circuit diagram using only NAND gates and minimum number of inverters. So it's okay to use inverters in your circuit here. Okay, so let's start by converting this circuit, and I will work on the original circuit and follow the steps. So the first thing that we need to do is to convert convert pure AND gates to NAND gates. Okay, so this one here, and then I need to cancel that with an inverter, right? And this one here, okay, and then I put an inverter to cancel it, but I have an OR gate here. Okay, so I put a bubble before the OR gate to cancel this bubble. Okay, because I want to utilize my inverter here to be the input of the OR gate in order to convert it to NAND gate. Okay, again, same thing here. All right, so AND gates are all converted to NAND gates now. What about OR gates? So I need to for this one. Let's finish the output because it's almost done. So I have to invert this and put an inverter here. Okay. All right. Now for this one, for the input here. Okay. I'll put a bubble here and then invert it. Okay. What's next?
Invert B and put 2 bubbles in the ORs.
Excellent. Yeah. So you're thinking ahead. Okay. Because you need a bubble here. Okay. But eventually you'll need a bubble here as well. So 2 birds, 1 stone. Okay. So this is clearly the minimum number of NOT gates that you need. Okay. All right. And then this is ready as well, because we can change this inverter to a bubble here. Okay. So the final circuit is this one here. Actually, A and B. All right. And this is F, this is E, and this is C. Okay. So this is the final circuit. Did I miss anything? So how many number? What is the number of inverters that we used here? 4 inverters. Right?
3, 4, yes.
4 inverters.
Doctor, I have a question about the must write NAND gate.
Yeah, go ahead.
So is this a rule? Is any like 3 input OR gate with NOTs, we can just make it NAND?
No.
3 input NAND?
Okay, so let's see if this is to answer your question. So I have, okay, I have X, Y, and Z, okay, and then I have bubbles here, and this is Z. So what is my Z algebraically? It's X complement ORed with Y complement ORed with Z complement, right? And using De Morgan's law, this is nothing but X, Y, Z, nothing complement. This is nothing but a NAND gate. Okay.
Okay. Yes, clear.
So it's but the thing that you need to worry about is that this one here, okay, is not the same as this one, as we said in the associativity part. Okay. F2,
yes.
then F2 does not equal to F1. Okay. I mean, even if they have the same input. A, B, C, A, B, C. Okay.
Okay.
Because of the associativity. And you can show this easily, okay? Either using truth table or whatever, okay? All right. This is all about the NAND gate, okay? Now, the NOR gate shouldn't take from us 5 minutes to explain, because most of the ideas have been discussed in the NAND gate, okay? And everything applies in the NOR gate, except that the rules are twisted a little bit, like when we explained min terms and then max terms. It's just an extension, okay? So now the NOR gate, first of all, the symbol of the NOR gate is this one, which is OR followed by NOT, okay? So this is the OR NOT symbol. And then you can also, by De Morgan's law, you can do it using NOT followed by AND, right? By pure AND. So you can invert the input of the AND, and follow it by AND gate. Okay, so this is nothing but a NOR gate. Okay, NOR gate. And again, you can prove that it is commutative and it is not associative like the NAND, and it is also universal. Okay, and we can go over the universality, proof of universality for the NOR gate. The NOT, okay, is implemented using this structure here, or you can do it using you have X here, and then you have a 0 here, and you NOR the 2, then you get X or the 0 complement, which is X complement. Okay, both are fine. Both are the same representation of NOT. Okay, or can be implemented using NOR followed by an inverter. Okay, because this inverter here cancels the bubble and you're left with only the pure OR. Okay, and okay, you can again use the same De Morgan's law. Okay, to change the inputs. Okay, or complement the inputs, and then put bubbles at the input of the AND gate. So this AND gate now is the other form of the NOR gate. Okay, so eventually X and Y, okay, which is Z, can be X complement NORed with Y complement. Okay, by De Morgan's law. All right. So let's take this example just to make sure that you guys can do it. Okay, let's do this example again. So let me copy this, and this time we do it for NOR instead of NAND, and you'll see that it is even simpler for the case of the NOR. Okay, so now we start with OR gates, which are simpler. Okay, so we change this to an OR, and then put an inverter to preserve the functionality, or take advantage of the presence of the AND gate here and put the bubble here. Okay, as part of the AND gate input. Okay, because eventually we'll have to change this AND gate to an OR gate. Okay, and then we have to also complement this and put an inverter here to preserve the functionality of the circuit. Okay, and this one can be pushed ahead, and it becomes like a bubble here. Okay, and then we have a bubble here and an inverter here. Okay, and that's it. So your NOR implementation of this circuit is nothing but you have here a okay, and NOR, and then B, NOR, A, B, and C. Okay, any question? Okay, so this is the NOR implementation. So if you compare this NOR implementation with the NAND implementation, so let's just count the number of gates here. Here we have 1, 2, 3, 4, 5. Okay, whereas in the NAND example, we have 1, 2, 3, 4, 5. Okay, both resulting in 5 gates. Okay, excellent. Okay, So now we do the same exam question, but now I'm changing this requirement to NOR gates and minimum number of inverters. Okay, so yes, guys, who can tell me what to do now?
Start with the OR.
Yeah, so I put a bubble here, and then a bubble here, right?
Yes.
And then a bubble here, and then bubble here. Okay, and then a bubble here and an inverter here. This is my X. Okay. Then worry about the AND. This one is done already. Okay. This one here, I need to put a bubble here. Okay, and then inverter. So D complement instead of D. And a bubble here. Okay. And an inverter. Okay.
Can you put the inverter before?
Just like what we did in the previous example, right?
Yes.
In the here, actually in this part here. Okay. For the NAND example. Okay, so we put it here. Excellent. So we take two birds with one stone, and then we put an inverter here to cancel both. Okay. And then here we have a bubble with a complement. Okay. So the final circuit is right. D. And this is okay. Okay, let's convert or compare the number of inverters in case of the NANDs and the NORs. Okay, between the two questions. Okay, this is 1, 2, 3, 4, 5. Okay, so this is 5 inverters. How about this one? 1, 2, 3, 4. Okay, 4 inverters. Somehow the NAND implementation here is better by 1 inverter. Okay. Okay, and this is come again.
Generally, the NAND results more less.
No, it's not. There is no rule for that. Sometimes it's that, and sometimes, except there is a rule for the 2-level implementation. Okay, sum of product. Okay, in sum of product, the NAND is the best implementation. It results in lesser number of gates, and product of sum, the NOR is the best. Okay, but for multi-level implementation, there is no rule for that. I mean, it could be that or this, depending on the problem. Okay. All right. Next time we are going to start the XOR gate. But before that, let's just do this. This is a quiz question. Okay. One of my old quizzes. Okay. Let's do this and convert this circuit to NAND implementation. Okay. So yeah, how do I do it? This one. Okay. With this one here, cancels. All right. And this one here, but I need another inverter here. Okay, and this one, but with another inverter here. So this is my F. Okay. Now, I have here an option here, right? Which option gives me the best alternative? So do I put this, for example, with this? Okay. This will result in one additional inverter, or push this forward. What happens if I push it forward?
It
Same.
splits into two.
It's exactly the same, right?
Yes.
Actually, yeah. I mean, it's going to be. Actually, no. It's actually. So this one is 2, but this one, if I push this ahead, then, and this one is not there, then I have here a bubble, which is not an inverter. It's a bubble. Okay. It's part of the NAND. Okay, and this one has to be inverted. Okay, so the previous option was 2 inverters. Okay, whereas this one results in 1 inverter. So this is a better option. You see that? So the previous option was like this. Okay, I have 1 and 2, right? Let's count them all. Okay, it's fine. 1, 2, 3, 4. Okay, whereas the other option is to push this forward. Okay, let me just erase it. Okay, erase it and then push it forward. Okay, so I have a bubble here now and an inverter here. Okay, so how many inverters total? 1, 2, 3 instead of 4. You see that? So this option is better than that option. Okay, so then you can draw the circuit yourself. Okay, using NAND only. So this question asks for NAND only without inverters. Okay, so even inverters, you need to change them to NANDs. Okay, so that's about the NAND implementation. Let me stop recording so that the lecture doesn't become longer than required.